do is motivate the linear operators. So we're going to leave this and just go back to differential equations, and this is an example that we do in 105B. But we do a lot more of it there. Here we'll just erase. Start with the example of a couple of springs, and a few springs and a couple of masses. We'll just do it using Newton's law. Our system. We've got, so we're doing linear algebra. But before we do the linear algebra, we just take 3 springs and 2 masses on a frictionless track. Draw a nice large. Now usually, in fact, next semester we're going to solve all these things with Lagrangian mechanics. But right now we're just going to use Newton's law. So we've got a mass, we've got a spring constant here, and we've got a different one in the middle. So let me remind myself how we do this with Newton's law. So what we're going to have is x1 equals 0. And at this point, the system's in equilibrium and all 3 springs are relaxed. Okay? Springs are relaxed in this case. So to get the differential equation of these, we could first of all just say m1 m1 x1 second derivative equals f1, and m2 x2 double dot equals f2. We don't know what those forces are yet, but that's the law. And these m's, m1 and m2 are going to be the same, but for the moment, eventually. But we can just write down m1, x1, m2, x2. Okay. So, what is the force on this first mass? If I displace this mass here to the right or left, the left spring is a restoring force. Okay. So the left spring gives me minus k x1. What about the right spring? Okay. That will so the force from the right side will depend on the relative displacement of these 2 quantities here. All right, and this M1 only knows about K prime, it knows nothing about this K over here, right? So it's just going to be minus K prime, X1 minus X2, because the relative displacement of these 2 will determine how much this spring has been compressed. And to check the sign here, you can say, well, good, if x1 is 0, right, then it's going to be negative times that is positive, it'll be plus k prime x2, because if x2 is falling out, we're pulling or pushing it. Okay. Good, so that's f1. We got to do the same thing for f2. We get minus kx2, again, restoring force from this spring right here, and the same argument before. This time with a plus x1 minus x2. So that's Newton's law for both of those. Okay, so is there a compact way to write these? We'll get the compact way after we just ask about the solutions. So these are ordinary differential equations, constant coefficients, and they're coupled. So we'll do a trial solution of the exponential. So let x1 equal a1 e to the I omega t, x2 equal a2 e to the I omega t. Omega is real, and we'll plug those into there and see what happens. See if we get a solution. This is a trial solution. See what happens when we plug them in. So, first of all, we take two derivatives of x1 and x2. And you see each time it brings down I omega. We've been doing this recently, and brings I omega squared. So x1 second derivative equals minus omega squared a1 into I omega 2. Same thing for second one. A2 into I omega t. And now we can go into these equations here and just plug in. You'll see we'll get a common e to the I omega t on everything that's going to cancel. Okay. So we get minus omega squared m a1. That's this right here. In fact, I'll stack on it. Minus omega squared m a2. And on the right side, we'll have minus k a1 minus k prime a1 minus a2, and we'll have minus k a2 plus k prime a1 minus a2. So far so good. Of course, it all hinges on this trial solution being right. But these were first order, I mean, these were linear in x1 and x2. Okay. So now we'll go ahead and simplify this some more. We'll take what goes together with a1 and what goes with a2. So we'll have minus omega squared m to the a1 plus k plus k prime a1 equals k prime a2, and on this one here, similar, minus omega squared m plus k, and the k prime is the a2, so plus k prime a2. This is an a1, by the way. A2 is equal to A2 is equal to K prime A1. So yeah, we can actually take this one all the way through, and we'll do minus omega squared m plus k prime. That's an a2. Take the second one. Equals k prime a1. And the a1 is k prime divided by minus omega squared m plus k prime. Okay, so I just substituted those in, and I've got times a2 again. So finally, we get minus omega squared m plus k prime squared equals k prime squared. this point, we can take the square root of both sides and get two solutions out of this. So I've just step by step gone through here. Let's see what the last step gives us. Minus omega squared m plus k prime equals plus or minus k prime. And I'm going to have two solutions. Omega sub plus, I think I got room right here. So omega sub plus is I take the plus sign, the k primes go away, and I end up with equals. In fact, I'll do omega plus squared equals k divided by m. Put a box around that. I'm going to hold on to that. And if I take the minus sign, I have, I take the k prime with the minus sign over here, get 2k prime. Omega minus squared equals k plus 2k prime over n. So these results we're going to hold on to. I'm going to redraw our system and discuss this. Okay. So yeah, this was just a flurry of arithmetic, so to speak. Once we did the trial solution of this, we just went in there and solved. Okay. So what we want to do next is see the form of these. But since this was a physics problem, let's quickly discuss what's going on here with our original model. So our original model, we've got these two masses here. And am I calling them, yeah, I'm just calling them both M. That's for good reason. K prime, K, M. So those of you who know the double pendulum is connected with a spring in the middle, that's a couple of you. I gotta bring it to class for everyone else. Okay. So this system can be realized if you have two pendula that can swing independently, be connected with a weak spring, or any spring. Otherwise, you just imagine you had maybe gliders on the air track connected by springs. So these two things that we're showcasing here have particular meaning. So omega sub plus square root of k over m. You guys recognize that as the oscillation frequency of a mass on a spring, right? So in that case, what you'd be looking at would be these two. I got this one back. It's got a k prime. These two masses going back and forth and leaving k prime untouched. Okay. What about this one down here? K plus 2k prime. Anybody describe the motion of the system with this frequency here? K plus 2k prime. If you flex your imagination. Apparently the middle spring is involved with twice its natural strength. Okay. What's going on here is that these two masses are oscillating against each other. So those are the two physical manifestations of realizations here. So they're oscillating against each other, and because the spring, the center of it is immobile, it effectively has twice the spring constant. Okay. So anyway, that was the physical treatment, and these were the algebraic steps I took. Now what I'm going to do is formulate this problem as a matrix problem, where it's actually much easier to oversee. Okay. Here, you kind of have to know what to do, But what I'm going to do is leave this picture up and just rewrite the. Actually, I can start here actually. So let me go ahead and leave these up, erase this, and. Right, the e to the I omega t just canceled, right? Canceled from every expression. So we're looking at these two equations, and we want to put them into matrix form. Okay, so discuss those. notes, I reversed the order, that's okay. So you guys have seen matrix multiplication before. And this is a nice way to motivate it. So we've got these written up pretty large. The right side equations can be written like this. K plus K prime minus K prime minus K prime. K plus K prime. And then A1 and A2 is a vector. So a two-component vector. And if you multiply this out, remember, row times column. So K plus K prime times A1 minus K prime times A2. Should have had them all on one side still. Oh, I see what I got. Here, let me write this out. I've actually multiplied everything by equals. Equals omega squared m A1, A2. So what I've done here is I've multiplied both sides by -1. And then you can see we've got, if we multiply with -1, I'll just go ahead and do that in red. So -1, -1. First row times column gives us this, K plus K prime A1, K prime minus A2. Okay. And the second one, minus K prime A1 plus, minus that minus is plus, K plus K prime A2. So yeah, that's the first step. So we have a matrix times a vector equals a vector here. Before we go on, how are you guys with the matrix multiplication? Back. You've seen those before? Yeah. So what we're talking about here, the way to remember it is it's row times column. Okay. Row times column, row times column. So why do I only have a single vector on the right side? This is called an eigenvector. So this is a really so yeah, when you have a matrix times a vector is equal to that same vector times some constant, you've generated an eigenvalue problem. So you can see that our two masses, 3 springs, generated a matrix multiplication and an eigenvalue problem all at once. Okay. So I'm just gonna, okay. So we could also say K A equals lambda A. That's the form of a matrix times a vector equals an eigenvalue times a vector. Just curious, when's the last time you guys saw matrices and eigenvalues?
Maybe one, I think.
How about you two also? Quantum's much harder. Quantum, they kind of assume it all, right? Okay, but yeah. Dr. Hall? So, yeah, so that's the eigenvalue, eigenvector equation. And what this matrix is a linear operator. That brings us into the linear algebra. This is a linear operator. This is a vector. We're going to see that we have linear operators on our function space as well. If you're in quantum, then you've seen that, right? But here we're getting it step by step. So linear operator, I'll just put this terminology here. Linear operator, and this of course is a vector, 2-component vector, but it could be more. This is the same vector, and this is an eigenvalue. So this is the equation with which you find an eigenvalue and an eigenvector. So what is it about linear operators? Yeah, let me write more down. So, okay, we did this step by step. Let's write the little matrix multiplication formalism down. Yeah, I'm gonna erase these too. So these have the form. So I'll just write here matrix times vector multiplication. So the idea is you've got k ij xj, j equals 1 to n. So you're summing over, and let's write under here, we'll go k11, k12, all the way to k1n, k21, k2n, kn1, knn. So that would be our matrix. Anything beyond 2 by 2 can be tedious. And then our vector will just use x, x1, x2, all the way to xn. So this is ith row of the matrix times our column. And if we're reading it off, say I equals 1, k11 x1 plus k12 x2 plus k13 all the way to k1n xn. So that's this row times column. You want to just start to recognize it. Right? We've been generating these kind of matrices in various situations. So that's a linear operation. So matrix times vector is a linear operation. And what does linear mean? So I'll just say K here is a linear operator. That's what we'll end with today. Because k x1 plus x2 vector equals k x1 plus k x2. Seems like the most trivial operation, but it has to hold true for a matrix times a vector. And the other reason, or that's the one definition, and the other definition is k times alpha x equals alpha k times x. You can actually put these both in one equation if you said alpha x1 plus beta x2, but we're going to spread apart. So these two properties define a linear operator. And what you're looking at is, in this case, we have a matrix and we have vectors, or arrows, so to speak, is n tuples. And you can actually we'll check the second one because it's the easiest one, but they're both easy. So k alpha x actually, you know what, let's put this in here for your notes. This is kx ith component. Yeah, actually, you can go back to that little section we got there. So ith row times the column. So if you take the matrix times the vector, which is another vector. This picks off its ith component. The way you see that is we've summed over all the j's and we've got the I that has been summed over. Okay. So now we'll do the same thing here. K alpha x ith component is going to be sum over K I j alpha x j. J equals 1 to n. And you'll see you can do the same thing for property 1 here. But yeah, alpha is just a number. Alpha is a complex number. So you can pull the alpha out. Equals alpha sum over Kij xj equals alpha k x y component. There's a proof. So these very basic properties, this one you would do exactly the same. And it proves that this matrix problem that we had is a linear algebra problem. The matrix is a linear operator. And of course, we've got the eigenvalue equation up there. So we're going to do this structure a bit more with vectors, and then we're going to take it into functions. And if you guys are in quantum already, then you've seen it, so that should bring stuff like that into focus. So that's where we're headed with this. Yeah, I wanted to, start with a purely physical case and take it all the way into the formalism, which is what we did. Good. All in the day.